On Tuesday, we introduced two approaches for transient stability analysis. So both approaches need to answer whether the system described by this model, which include both ordinary differential equations and algebraic equations, can be stable after some disturbance. And we mentioned there are two methods. The first type of methods are called derived method, and it is based on the Lyapunov second method for stability. And the second method, somehow indirect method, which need to do time domain simulation first, based on some initial state to solve the initial value problem for any desired period of time. And if the system, all the generators stay together, which means the synchronism is maintained, the system is stable. If any generator flies away, it will be unstable. To be able to solve the DAE model, we need to utilize some integration method. It can be an implicit method or explicit method, and to finish the simulations. We also mentioned for the implicit method, that one do not have numerical stability problem, but for the explicit method, it will have a numerical stability problem. Numerical stability is defined as, so if a system is stable, itself is stable, but when you use a numerical solver, try to estimate the trajectory, if it doesn't have numerical stability problem, and the simulation result will be also stable, okay? But if you have numerical instability, your time step need to be small enough, otherwise the simulation result can be unstable, although the original system is stable. Okay, that's a very brief summary on what we learned. We ended at the implicit methods. Popular method is a trapezoidal rule method or trap. You can find this method in most of the simulators. So we mentioned the simulation, you just try to start from an initial state at the initial time. You try to, over a certain time step of h, you want to predict the next point. So this black curve will be the nonlinear function you're going to calculate how the state variable to change. The trapezoidal rule method is just you draw the nonlinear functions. So in order to calculate how the state variable to change, you need to integrate the entire area under this nonlinear curve. But we can use a trapezoid to approximate that area, because we only just miss very small area, so that doesn't cause much error. And definitely, if you go to next step, you are going to do, you will keep doing the calculating the area of a trapezoid, then to give you approximate result. So this is the method. It calculates the slope at the starting point and also the slope at ending point. And using the both slope, they will calculate the average. Okay. And that will be the estimated the new state. Even it's not exactly on the black curve, but it will be much better than using only the slope at either the starting point or ending point. So if you compare this one to one of the explicit method, like modified Euler method, it's very similar. It has almost same formula, but only difference is to calculate the second slope at ending point. It doesn't use exactly that ending point value. It uses a predicted value. The predicted value is obtained from a forward Euler method. But the benefit of using this modified Euler method is you don't have to iterate. You just you calculate the first slope, and based on the first slope, you have this point, and use this point to calculate another approximate slope, and those two slopes you can find some approximate one. So it's very straightforward. You don't have to go back and forth. But for the trapezoidal rule method, because the future state appears on both sides of the equation, so you have to solve the entire equation as a nonlinear equation using like Newton-Raphson approach. If you compare to another implicit method, which is simplest implicit method, is a backward-Euler method. Backward-Euler method only use just a single slope, but that single slope will be taken at ending point. Compared to the trapezoidal rule method, the backward-Euler method, instead of using the trapezoid, it uses a rectangle area to approximate the total area under this nonlinear curve. Implicit method has no numerical stability issues if the system is stable, which means that the curve will be bounded. So if your system behave as a stable system, even the oscillate near the equilibrium point, the simulation result based on trapezoidal rule method will also show maybe oscillatory curve near the equilibrium point. It may be not exactly same as the true trajectory, but it will not be like divergent from the equilibrium. So trapezoidal rule method definitely is better than backward Euler method, although they both are implicit. But for explicit method, you have to use a very small time step to make sure the simulation result can be bounded if the system is stable. Okay. So you may feel the implicit method is better than explicit method. That answer can be yes if you talk about the numerical stability. If numerical stability really your concern, which means your system, which means you don't worry about the time cost to calculate the simulation result. You want to make sure you have a numerically stable result, and the result, if the system is stable, the result is won't be unstable. If that's your focus, you can choose the implicit method like trapezoidal rule method. But if the simulation speed is your goal, the explicit method is not too bad, because although those two have the similar formula, okay, but the modified Euler method only need to calculate one slope, then second slope, and then move to the next step, finish this interval. Okay, but for trapezoidal rule method, you need to solve this equation through some numerical iteration until like when you plug in the value for this k plus 1 and calculate another value of sk plus 1 from the left-hand side, those two have to be close enough, you can move on. If that two always has certain gap higher than your error tolerance, you need to keep iteration. So which means, although there's single equation, but in order to solve this equation, you may take a large number of iterations. So that can slow down your process. But you may argue, I can take a longer time step. I can make time step longer, but I will do more iteration for each time step. That's implicit method. But for explicit method, you don't need to do iteration at each time step, but you need to make time step be smaller. Okay. So the general conclusion is if the system is really steep, the numerical stability will be a huge concern because the system trajectory may have, they can have some slow dynamic, but on top of slow dynamic, there's very fast dynamic. Then when you simulate such a system using explicit method like modified Euler method, the time step has to be very small, right? You have to track the fast dynamic. That can be very slow. But if that fast dynamic is not important to you, I really want to capture this, the overall the trend of the dynamic, I can use trapezoidal rule method, take a large step simulation. Okay. So that's some idea to choose between the implicit or explicit method. In the project, the MATLAB code provided with the project is based on the Runge-Kutta false order method. But if you do that additional step to test, to benchmark with the PSSE, TSAT, or DSALEN, or any other simulator, any simulator provide at least modify Euler, Runge-Kutta method, false order method, and the trapezoidal rule method. So those methods are all available. Feel free to do some tests, just compare. So this is an example to show if the system, if you use isolation method, by changing just a little bit of the time step, you can generate a very different result. So that only happens with trapezoidal rule method. But for trapezoidal rule method, it can take a very large time step, but it still can give you good result. For this case, the trapezoidal rule simulation method is same as the modified Euler with very tiny time step. But because this system is not very steep, it's only just the same system in your project, only have 4 generator. But if that dynamic has a lot of like a very fast dynamic on top of those curves. For instance, one generator become an inverter-based resource with a lot of power electronics. So there will be some electromagnetic transient dynamic at millisecond or microsecond time scale. Then that time step will be an issue. You cannot do that. You have to make that time scale step to be comparable or smaller than your fastest time constant. Then you can maintain the numerical stability. Trapezoidal rule method will be better. Only have numerical stability problem, but it may just lose those detailed dynamics. You still capture the full trend, but the trend of the dynamic, but you're going to lose some detailed dynamics. Okay. All right, so that's what we need to know about those methods. Let's continue. So let's talk about how to simulate a multi-machine system. So the system is modeled by the ordinary differential equation and the algebra equation. There's many different ways you can write down that set of equation, but typically you include all the dynamic devices into the first equation, first ODE. And in the second algebra equation, that is to mainly model the network. So it's more like just the power flow equation. So the Yn is the node admittance matrix. V is vector of all the bus voltages, and I is all the the current injections from all the buses. So it can be considered as a nonlinear function of a state variable and the voltage vector. So how do we solve this set of DAE? So we can solve the ODE using the either explicit or implicit integration method, like the ones we already learned. And then you can solve the algebra equations by using such as the Newton-Raphson method to solve power flow. It's similar to what you do to solve power flow. Then you need two methods, right? The first set of method is integration method. Second is just a nonlinear solver. So how do you do the simulation? So there are two schemes to interface the solutions from ODE and the solution from AE. The first one is called partitioned or alternating solution scheme, which means you solve ODE first, and any variable in the AE will be considered constant. Then you solve ODE first, and then pass the result to AE. Then you solve AE again to using the new result from ODE. Then pass the result back to the ODE. So you just iterate between the numerical integration solver and also the nonlinear power flow solver. Another scheme is you just solve them all together. For instance, if the ODE is simulated using the trapezoidal rule method, so it can be translated into a set of algebra equation. So finally, you only just need to solve the entire, the whole set of algebra equation using Newton-Raphson approach. So I will briefly talk about both ideas. So the first scheme is a partitioned solution method, and so when you solve the ODE, you assume all the bus voltage to be constant. So this one doesn't change. So you only just want to update those state variables. For instance, if one generator connected to a substation, when you solve the ODE for this generator, you treat the substation voltage as constant. you just simulate this generator on its own. Then the simulation will tell the state variable, the change on the state variable for one time step, then give that value back to the network. The network will use this state variable for some maybe control to update the power flow solution and to solve the voltage. Then you'll go back. So after one cycle, you will finish one iteration. So for each time step, you need to do such an iteration. Okay, I give you a very simple example. For instance, if we take a classic model for generator, and we simulate a power system with some generators, and there may be some other dynamic device like this motor. This means motor. The motor will have another set of differential equation. So at each bus, we assume the bus voltage and also the current injection into the network. And the network is modeled by either we use this linear equation or we use this nonlinear equation. So either one is fine to solve the power flow. Okay. So let's assume the first step. The first step, we assume the voltage to be constant. So this voltage to be constant. And we solve this whole set of equation for the generator. And our target is to calculate this current for one time step. Then I give this what current as well as the state variable to the network. Then I update this vector of current. Then I want to solve this voltage by using power flow equations. So there are two ways to solve this equation. The first one is I take this formulation, I will solve it as a power flow, like Newton-Raphson method. There's some other simulator, they don't solve this nonlinear equation. Instead, they solve this linear equation. Although this linear equation is not accurate, they only just need to solve the inverse of this Y matrix, and from current to solve the V, right? You just both sides, assuming both sides, you just multiply by the inverse. You'll be able to calculate V. Just solve linear equation. And solve the linear equation, you'll pass the result back to the ODE, the integration method, like Euler-Runge-Kutta method, and they just update the voltage again. You do that. But each time step, such iteration will maybe take 5 or 10 times iteration. So that's how they simulate the system. A next strategy is to solve the whole set of equations at the same time. We need to translate the ODE into some algebra equation. We can use trapezoidal rule method. Based on trapezoidal rule method, so n just indicate the current state vector. N plus 1 is the next step, next time step. So this is just the trapezoidal rule formula. Okay, you see you have the future state on both sides of the equation. So you add the power flow equation here. So now this equation, the whole set of equation become algebra equation. It's not differential equation anymore. If you treat as n plus 1 as some n-th variable you want to solve, okay, it appears on both sides of equation. You can rearrange the equation to put everything on the left-hand side, and the right-hand side you only put 0. So that make it formulated as a standard like nonlinear equation. So next you can try to solve this equation. This equation is just to calculate the value, the state vector for next or single time step. At each time step, you need to solve this equation similar to solving power flow equation. When solving this equation, you need to take some iteration, right? You can take some iteration. You can start from 1, 2 until maybe large enough iteration until the n plus 1, the state vector doesn't update or the voltage doesn't update. So this is Jacobian is just this nonlinear equations Jacobian and to it's similar to the slope for the one-dimensional problem. Okay, after a number of iterations, you will convert to some x and some v. That is only the values for the next time step. Okay. Yeah. So this is the last slide of the simulation, and we can move to the derived methods. So for derived methods, we need to start from the theory. The fundamental of the derived method is based on the Lyapunov stability theory. So in mathematics, the stability theory concerns the ability of solutions to set up differential equations, or it can be considered the stability for trajectory of a dynamic system under some perturbation. So definition, the mathematical definition of stability, such as the Lyapunov stability, is defined as so if you consider autonomous nonlinear dynamic system, so if the vector field with which the nonlinear function f has an equilibrium at xs, which means if you plug in the fx, so the f is 0. Okay, so which means the state doesn't update. So if you plug in the equilibrium, so the state doesn't update, it doesn't move. So that will be the equilibrium. If this equilibrium is said to be Lyapunov stable, if for every small positive number epsilon, there exists another positive small number delta. Usually this delta is smaller than epsilon, such that if you release the state within a small enough neighborhood of the stable equilibrium point, and that system state will never escape the neighborhood of epsilon. So no matter how small epsilon you gave, actually small number of epsilon, I can always find the delta. I only just need to make the system initial state to be close enough to the equilibrium within the distance of delta. It will never go outside of epsilon. So that's the definition. Then if this is true, that equilibrium is called stable equilibrium. And after some perturbation, the system can safely transition to this stable equilibrium. We can see this trajectory to be stable. If we visualize what happened, so if I gave this epsilon, okay, so in two-dimensional, I can draw this circle. I want the system to stay within this epsilon. And I can find another small number delta. Okay, delta is smaller than epsilon. It's closer to the equilibrium. But if I release the system state within the smaller circle delta, it may sometimes go outside of the circle of delta, but will never escape the circle of epsilon. It will stay within the envelope of epsilon. If this is true, the system is stable near this equilibrium point. Another way to visualize what happened on the system state and the disturbance, we can use this analogy. We have a concave surface. So at the bottom, that will be the equilibrium. Okay, and I don't want there's a ball moving on that surface, but I don't want the ball to move higher than this limit. Okay, I only just need to release the ball at this location, and they will just oscillate in the surface. If there's any friction, eventually it will go back to the equilibrium. If there's no friction, it will just oscillate forever. But that's fine. It will never escape from this limit of epsilon. If that can happen, I can safely say that equilibrium point is stable equilibrium point. The next thing I just want to check, either do simulation or use some direct method to figure out whether I release this ball, it will safely go to this one. Definitely, If I release the ball here, I don't know. Okay. Maybe if the system doesn't have friction, when it's go down, it will maybe go to the other way about the same height based on the conservation of the energy, which means if I release this ball at that height, it may escape the region of epsilon. Okay. But if the system has enough friction, it may not reach this height. That means, so if I release this ball here, right? But system has a lot of friction, which means a lot of mechanical energy will become heat. And maybe when we move to the other side, and this is the highest position it can reach, then the system is still stable. Okay, so but that will be the next question. That will be the question about whether the dynamic of the system is stable or not. Okay. How do we judge the stability of the system? We can utilize the Lyapunov stability criterion, which is also called Lyapunov second method. So we still consider this dynamic system. Its equilibrium xs is stable if there exists a positive definite function Vx. We call it Lyapunov function, such that its time derivative is not positive. So that is a statement of this Lyapunov stability criteria. So positive definite, which means this function is basically positive. Okay, it can sometimes be zero, not positive, but it can never be negative. It can be zero, but zero only appear on some very rare, very few locations, such as the equilibrium itself, which means because equilibrium is stable, if this function is only zero at that equilibrium, we don't need this function at all. We only just want to use this function to check the stability when the system is not at equilibrium. So, which means such function is generalized energy. It represents some type of energy, because energy has to be positive definite. And also energy has to be, the time derivative of energy cannot be positive, because energy can be dissipated but cannot grow. If you model everything, model environment, if there's any friction, the mechanical energy will decrease, will gradually become heat, will be dissipated, but the energy can never be generated from nothing. So any energy has to be time derivative, will have non-positive time derivative. Okay, so to use some mathematical equalities to represent those two conditions, for positive definite function, which means the function can be positive or zero, but if it's zero, it has to be at the equilibrium point. If it's not at zero, it will be positive. Okay, so think about the analogy we use in this slide. So if that energy represents the total energy of the ball, it only have zero energy at the bottom point. But if it's not at the bottom point, the potential energy can be positive, so the energy will not be zero. So definitely the energy of this ball will be some type of a Lyapunov function. The second condition, the time derivative of energy has to be non-positive. It does not increase with time. It can only decrease or stay the same if it's at equilibrium point. So if we want to make sure any trajectory when it's not too far from the equilibrium point can always go back to the equilibrium, we call this stability as asymptotic stability. So if this time derivative is negative definite, which means it's negative if it's not at equilibrium. At equilibrium can be zero, but if as long as it's not at equilibrium, it will be negative. So if I move, so just give you one example. So if this surface is like this one, okay. So if the ball is moving on the surface, it has to be negative definite. So the bottom point has to be asymptotically stable, because the ball will move down. It cannot stay on that surface. But if there's another surface, which is something like this one, okay, so it's possible you can put the ball there, right? it has local tangent be really flat, so the ball can stay there. Okay, but as long as it's still stay inside of this region, doesn't escape the region, it's still stable. But if it require asymptotically stable, really want the ball can always come back to the equilibrium. So next we can talk about the transient energy function method. Transient energy function method is basically just a approximate version of a Lyapunov stability criteria, because finding Lyapunov function which satisfy the both condition here may not be easy for very complex system. For very simple system, you can easily find that function. For instance, if we study this ball moving on that surface, we simply just let the energy function or this Lyapunov function be the total energy of the ball. So that will be Lyapunov function. But if you study a large power system with generators, power electronics, controllers, so how do you define the energy? So that you may not be able to find the Lyapunov function, but you can find some approximate Lyapunov function. And as long as that function is basically meet those two conditions, okay? Maybe may violate this condition only for very certain scenario, but you don't really care. Or then you can still call such function as energy function. So we still use that analogy, a ball rolling on the surface. In order to check the stability, we need to know, like this is an analogy, okay? So the bottom one is a stable equilibrium point. And this surface will have some the rims or edges on the top, but you can see in some direction it can be higher, but in some direction it can be lower. Okay, so the height of the rim is not evenly distributed along the edge of the surface. Depending on which direction the ball is moving, you need to make sure there's some limit and the ball will not escape this surface. The two things you need to check. The first is the initial energy of the ball. So using this analogy, if we consider mechanical energy, it will have kinetic energy and potential energy. VKE is the kinetic energy and VPE is the potential energy. Okay, so let's assume there's some disturbance. After disturbance, the ball is moved from the bottom point to some location here. Because it's not at the bottom, so it will have some potential energy. And because it's moving, it will have some kinetic energy. So the initial energy can have both the kinetic component and potential component. And the rim head of the surface or the ball, that one is actually tell you the critical energy, the maximum value you can have for the energy. Okay, so for instance, if my ball is moved to this rim, to this point, and reach the zero speed, so what happens is this ball will move back. It cannot escape. It has to have a little bit net energy, additional energy to move further, because if the speed has to be not zero, it can move further to go outside of the surface. If the speed decreases to zero at this point, it will come back. Okay, at least it will stay there. It won't escape from this ball. So the potential energy at that point will be the limit of the energy. We call that critical energy. So if it's just less than the critical energy, it will come back. If it's higher than critical energy, it will escape. And that critical energy can be estimated by the potential energy at that point. But because you see this point is higher than that point, right? So if you move towards that direction, the critical energy can be lower. So it really depends on the direction of the ball based on its initial condition, based on the initial speed. So to summarize the ideas of a transient energy function method, if you want to apply this method to power system. Initially, the system operates at a stable equilibrium point. We call it SEP or XS. When the fault occurs, the system gains kinetic energy VKE during the fault on period, and potential energy VPE due to the network change. What does this one mean? It means, okay, before I move on. So it means at the beginning, before the fault, that's the location of this ball, and the ball, this ball is stay at the bottom of that surface. But after you trip the line, which is like earthquake, it's not, the structure of the network is somehow changed. So the surface become this one. So relative to the new surface, the original ball, although it has zero potential energy at the bottom, but it gains some potential energy. And also because of the earthquake, the ball has some speed. So it will have both kinetic energy and potential energy. Okay. If it's a temporary fault, the surface doesn't change. The potential energy may be the same, but kinetic energy will be different. It will have some kinetic energy. So after fault clearing, the kinetic energy is gradually converted to potential energy, right? So will, the ball will become higher and higher. To maintain stability, the system must be capable of absorbing remaining kinetic energy while transitioning either back to the old stable equilibrium point or a new equilibrium point. Okay, for this case, the new equilibrium point will be here, right? So the old equilibrium point is not applied anymore because the surface has changed. For a given post-disturbance network configuration, there exists a critical maximum amount of transient energy, V critical, that the system can absorb without losing a synchronism. Therefore, assessing transient stability at the fault clear state, for example, S clear, requires first we need to define a transient energy function. We can estimate the total energy the state has after fault is clear. Then we compare this initial energy to that critical energy, which is the limit of energy. So if it's less than the limit, the system will be stable. Okay, the distance to that limit will be the stability margin, transient stability margin. So this is the whole idea of a transient energy function. So in the following slide, we start from a single machine infinity bar system. Okay, we figure out what the energy function look like. Then we gradually move to a more complex general system with many generators. Okay, so let's take a look at the phase trajectory of a single machine infinity bar system. So it can be modeled by the two swing equation plus another equation tell the electric power. So if you can merge those equations to eliminate the speed, you get this second order differential equation. So it's similar to the equation we use for studying small signal stability, but here we keep the nonlinear term. We don't linearize this atom. If you linearize that atom, that will become a synchronizing torque or synchronizing power. To solve the equilibrium, we simply let those two derivatives be zero. And to solve this algebra equation, so we have two solutions, right? The first solution will be has smaller angle, we call it stable equilibrium point. The other one is equal to 180 degrees minus this stable equilibrium point angle. That one will be unstable equilibrium point. If you simulate the system, give system random initial states and do the simulation, you'll be able to visualize all the possible trajectories in the phase plane. X is about the rotor angle, Y is about the speed of the rotor. So the green dot indicate the stable equilibrium point, and red dot indicate the unstable equilibrium point. So why are they many multiple stable or unstable equilibrium point? Because at a stable equilibrium point or at both equilibrium points, the speed deviation has to be 0, right? But the angle can be added by 360 degree or 720 degree. So it will still be an equilibrium. So which means within the range of angle from negative 180 degree to positive 180 degree, you'll be able to identify one stable equilibrium and one unstable equilibrium, which is taught by those two equations. But if you add 360 degree or subtract 360 degree for both equilibrium, you'll get another set of stable, unstable equilibrium point. But in the first place, you actually put any initial state. It can, if you release maybe from any arbitrary initial state, it may finally land it to either one stable equilibrium or maybe the other stable equilibrium. But if you take a look at those trajectory, we can somehow draw the region. This will be the stable region. Go through one unstable equilibrium point, which means if you start from any point inside of this region, will never escape, but it will always go on a closed orbit. This boundary is considered somehow marginally stable condition, which means it will pass through this unstable equilibrium point, but it's like moving around the edge of that surface. But if you release anywhere outside, right? So you can imagine this one will move in this direction. The frequency will go up, the speed will go up, and angle also increase monotonically. It will never be trapped by any stable region. And this is another stable region. Okay, so we can color that region. So that will be, it's also called domain of attraction of that stable equilibrium point. So for this case, we assume damping to be 0. Okay, so such as you can stay on the closed orbit. But if you increase damping, what happens is if you start from here, it will gradually go to that stable equilibrium. So if we draw the trajectory, it will be something like this one. So if we start from this point, if you compare the first figure, that starting point will be somewhere here, right? So without damping, it will just become further and further from this region. But in the second plot, if you start from here, due to the friction, so we'll move into this stable region and finally go to the stable equilibrium point. So the stable region is extended to be larger. It's not closed region as the first case. It will be, they also add another channel. So you can move, it can be attracted by that stable equilibrium point. So similarly, if I start from here, that will be trapped by another stable equilibrium point. But if you start from here, it still become unstable. So when you increase the damping, that makes a stable region be extended to include more possibility for the system to maintain stability. What if you make the damping even larger? You make a very large damping. Eventually, every state has transient stability because any state will be trapped by some of the stability region. For instance, if I start from here, it will move this way. If I start from here, it will move that way. So what about here? It's not trapped by either this one or that one. It cannot go, but it will eventually trapped by this one. So when your system has enough damping, although damping is usually considered for a small signal stability, but if the damping is large enough, eventually system can be very stable. So now let's see what happened on a single machine InfiniBand system subjected to a step change in mechanical power, for example. We studied this one in the small signal stability session. So we define the gap between the mechanical power and electric power as the accelerating power, PA. This is like the force in the Newton's second law to determine how the angle to speed up. If we have a step change on the mechanical power, all right, so the system equilibrium point will move to this new point because the equilibrium will be the new mechanical power intersecting with the power angle curve PE. So we will have two intersection points. So this point will be stable equilibrium point. The other point will be unstable equilibrium point. So when you have this step change, the system will move from A to B. Okay. So at point B, so the electric power will be equal to the mechanical power. Because the rotor's inertia, when you add this step change, the angle cannot change, cannot instantaneously increase. It has to gradually move up. Because the new PM, new mechanical power is higher than the electric power. So the generator will be accelerated. So the speed will increase from 60 Hertz. So when it reaches B, and at the new equilibrium point, and the accelerating power becomes 0. But keep in mind, so during this process, the speed increased from 60 Hertz all the way until B. So right now, the frequency is higher than 60 Hertz. Because it's higher, so the angle will continue to increase. So which means it cannot stop at B. Even the power increase at one step to B, but the angle will gradually increase and to B and cannot stop, will move further. So that actually explains what happened here. So it will oscillate the angle. So second step is move from B to C. So when the angle is higher than the angle of the new equilibrium point, so the accelerating power becomes negative, which means the speed will decrease. Okay. Even the angle can still continue to increase. So it will increase until the speed is equal to the 60 Hertz again. That will be the point C. So at point C, the angle cannot increase further. It will reach the maximum value. So that's what happened here. So from A, B, and C, it finished half of the cycle of the swing. It finished this pass. And starting from C, it will come back because the rotor will decelerate. Because right now the point C is above the new mechanical power. So accelerating power has to be negative, which means the angle will decrease, will become less than 60 Hertz, and angle will decrease. So it will come back. So if we ignore any damping, any resistance, so the angle and speed will oscillate forever at constant amplitude around the equilibrium point. So this one will oscillate forever at same amplitude. So let me ask a question. So when does the speed reach its minimal value? So A will be the synchronous speed, okay? B will be the maximal speed, and C will be the synchronous speed again, and then it come back. When does the generator reach the minimal speed, the lowest speed? It will be at point B. So the first time it passes through the point B, it has the largest speed. When it come back, it goes through the point B, will have the smallest speed. Okay, you can do the differential of this curve. Yeah, this curve is angle. You do the differential. The speed will be slope, right? This point will have the largest slope, and this point will have the negative largest slope, so the smallest slope. So they both correspond to point B. Those 2 points. Okay, that's summarized in this table. At point A, the accelerating power is positive, and the speed is a similar speed, 60 Hz. They will go up, and angle increase. When it reaches the point B, the accelerating power becomes 0, and the frequency of speed reaches the maximum value, and angle further increase. And at point C, the speed will go back to the similar speed, and angle reach the maximum. And if you further write down to document what happened when it come back to B, the next one will be omega R minimum. Huh? Oh, sorry. Yeah, thank you for reminding me. All right. So next question. Does angle vary sinusoidally in time as a sinusoidal function? I think it's passed away. There's some copy there. This is last time. This is Tuesday, and also that's Thursday.
Thank you.
Right. Okay. So next question: is this curve like a sinusoid? Okay. So answer is this curve is not sinusoid. Only when the disturbance is very small, almost 0, this curve becomes sinusoid. Otherwise, not sinusoid. So before I move on, just quickly give you an explanation. So what this curve look like? So this is the nonlinear equation for the single machine infinity box system if we only keep angle as the state variable. So it's a second order nonlinear differential equation. So if we consider the deviation from the equilibrium point, so we'll transform the equation to this form. So it looks complex, but if you compare this one to the harmonic oscillator equation, you can tell this whole bunch is basically similar to that frequency. But because this entire coefficient is not constant, it depends on the angle deviation. So which means when the single machine infinity box oscillate under large disturbance, so that oscillation is not linear. If it has frequency, the frequency is not constant frequency. It's a varying frequency. So let's give the system some value. Like if we assume that's inertia, we assume a 0 damping, we assume maximal power, and also the equilibrium point. And so which means that equilibrium point will have angle 30 degrees. So if we give system a small disturbance, the system will oscillate around the 30 degree. At maybe the amplitude is only 10 to 15 degree amplitude. So the waveform is approximately a sinusoid. Okay, that's for small disturbance. But if you increase disturbance, the waveform will look like this one. So this is called the marginally stable curve, which means if you increase the amplitude only a little, the system will become unstable. So this is a maximum amplitude. The single machine infinity box system can oscillate without transient instability. So the waveform is not sinusoid, and also it's not symmetric about the amplitude. That one actually can be explained if you consider this phase space trajectory. When it oscillates around the stable equilibrium, it's not symmetric. Okay. When it gets closer to the unstable equilibrium point, that amplitude can be bigger, and the other side is smaller. So it's not symmetric waveform. But we can still calculate the frequency of the bottom waveform. So we need to calculate the first time and second time. The first time is how much it takes to swing up, and the second will be swing down. And the frequency can be defined as 1 over the total period. The total period will be the T1 plus T2. And each time can be calculated by solving this equation. This is elliptic integral of the first kind. So it doesn't have analytical solution. You can only use some numerical method to solve it. But if you solve this equation, you will get this curve. Okay, the x is amplitude of oscillation, and y is frequency of oscillation. So if the amplitude is 0, which is like small signal stability, that will be at stable equilibrium point. So the frequency here, it will give you the natural frequency, omega n or fn. But when you increase the amplitude, okay, maybe to this level, so the point will come to here, which indicate the frequency will drop. When you reach to unstable equilibrium point, the trajectory is not periodic anymore. So it become transient, become unstable trajectory. So it's lost the definition. It will lose the definition of a periodic behavior. There's no definition of frequency. The frequency becomes 0. So using this curve, you can actually, based on the amplitude, you can measure the stability margin of the system. All right, so we should be able to, let's finish this slide. Okay, so let's talk about equal error criteria. So this is the transient energy measured similar version for single machine feedback system. So next we want to find out a way to define the transient energy function for single machine feedback system, because we want to study the stability. We know the initial energy compared to limit, we can know whether system is stable or not. Analogy of a single machine feedback system will be a pendular subjected to a constant torque. So assume this pendular has a weight of mass m connected through a stiff bar. It's not a link or not string. It actually cannot change the distance. The length will be length of L. And I can add a constant torque. Okay, so which means if this ball is not oscillating and it will stop at this line, this will be the stable direction. Okay, it will deviate from the vertical direction by angle of delta S, and is placed in the gravitational field. So if we use Newton's law, and it will be Newton's second law, the left-hand side will be a moment of inertia multiplied by the angular acceleration. The right-hand side will be the constant torque, subtract the torque due to the gravitational field. The torque of gravitational field, they basically just you calculate because the gravitational force is downward, and you multiply by the distance, okay, to the vertical center line, so you'll be able to calculate this torque. Okay, so if you compare this equation to the single machine feedback system, they have exactly same form. So which means single machine feedback system can be considered as a pendular subjected to a constant torque. If the synchronous generator has no mechanical power, that will be same to a conventional pendular. So for this pendular, you can calculate the kinetic energy and potential energy. Kinetic energy is defined to be a function only depending on the speed of the pendular square. So which is typically defined as half of the moment of inertia multiplied by the angular speed square. Okay, that's the definition of kinetic energy. Potential energy is defined to be if you move the ball from the equilibrium point to any location, how much work you need to do. That work will be the potential energy. Okay, so because right now there's a constant torque, you need to do two work. One is try to one is against the gravitational force. The second is against the constant torque. So there will be a two work component. Together will give you the potential energy. Okay, so we know the kinetic energy and potential energy for the pendular, and the total energy can be considered as transient energy function for single machine infinity bar system. We just learn from those two formulas to construct the transient energy function. So we just define the transient energy function to be a kinetic energy only depending on the angular speed squared, plus potential energy only depending on the angle. Okay, the kinetic energy will be like this one because this part is compared to the moment of inertia, right? This item and that item is same. So there will be a kinetic energy. A potential energy we just learned from the potential energy of the pendular we have this formula. The next question is how do we calculate kinetic energy? If we don't want to simulate, if you do simulation, you can know the speed at any time. But if you don't want to do simulation, because we're learning the direct method doesn't want to do any simulation. How do we estimate the kinetic energy? Okay, one way is we can try to solve what this speed, the speed square is. Okay, so by utilizing the chain rule of a calculus, we know if we calculate differential of this item, using the chain rule, you do the differential for everything in the parentheses as one variable. Okay, then the next step you do the derivative or differential of what's inside the parentheses. That's a chain rule. Remember, you do the chain rule means basically is, yeah, you do everything. You do the whole derivative, which is like the first derivative with respect to g, and then you do the derivative with respect to x. That's chain rule. So from the chain rule, we know the differential of this atom. So we only just need to integrate this one. So we get this one basically just proportional to differential of the angle. So kinetic energy will be just integrating this one for angle from initial angle to any delta angle. So it will be this one. So that's a formula to calculate kinetic energy without doing any simulation. Okay. So when the angle reaches the maximal value, which is the point C, so the speed will be 0. Kinetic energy also has to be 0. Then we'll know this function has to be 0. So this function is the integration from initial angle to the maximum angle. We partition this integral into two parts. The first part is we only just integrate from delta 0 to point B. So this is like from A to B. The second is from B to C. And that one corresponding to the integration is, the first one is the area under this PM1. That's like small, similar to triangular area, but it's not triangle. And the second part is that area 2, above the new equilibrium point. Okay, so we have a red area and blue area. The meaning of the red area is the kinetic energy gained by the system from A to B, because this process of accelerating from A to B, the accelerating power has been always positive. So we will gain some kinetic energy. And the region blue region is a potential energy at C relative to the new equilibrium point. And here we prove the A1 has to be equal to A2. Those two energy has to be equal. Even the shapes are not exactly matched, but they, based on conservation of energy law, if there's no any friction, no loss, those two areas have to be equal. Okay, so this gave us a way, based on the transient energy function defined for single machine infinity bar system, we can study the transient stability. So that is called equal area criterion. So stability is maintained only if the accelerating area A1 is smaller than the maximal decelerating area A2. For this case, A1 is equal to A2. But maximal, what is the maximal decelerating area A2? It is entire area above the new equilibrium point. So this is a maximal decelerating area. So accelerating area is determined based on disturbance. Once you determine disturbance, that accelerating area, the red area already decided. But the blue area depends on the system. So above this equilibrium, if you have large region which is large enough to cover the green region, the system will be stable. Okay, to slow down the system, to move it, to make it back, you only just need to utilize part of this decelerating area to be equal to accelerating area. Okay. Some more explanation. So if angle reaches the unstable equilibrium point, so the decelerating area will be smaller than accelerating area. So one case will be if you increase the mechanical power too much. If you increase by a very large step, so this whole area will become accelerating area, right? And the new decelerating area will be will be this smaller area. If that smaller area is less than the red area, the system will be unstable because it doesn't give you enough energy to decelerate, which means after disturbance, the system gain the total energy which is too large. It doesn't have enough potential energy for the ball to slow down. And so once it reaches the edge, it will continue move to become unstable. Okay. And which means the size of disturbance really matter for the transient stability. Okay. All right. So this question you can think about: what if the damping is not zero? What happened to the equal area criterion? So we'll continue on next Tuesday.